Dear colleagues, dear organization committee, we are grateful for our possibility to present our results on this conference. We propose you our new results on building upper bounds for probability of success of double spend attack for one of the modifications of proof of stake consensus protocol on blockchain, so-called proof of stake with checkpoints. Since 2008, there were a lot of investigations of different consensus protocols on blockchain about their security against different attacks. As for double spend attack, we may name several works devoted to security against this attack. First of all, this is Nakamoto's article, his single article in 2008, which gives a general view on blockchain. He also gave them tools to increase security against double spend attack, and also estimated probability of the success of this attack. But unfortunately, his results, those concerning probability of attack, his results stand out to be wrong from a probabilistic point of view. The first completely proved results were obtained by Grunspan and others in 2017. They get results of probability of double spend attack for blockchain with proof of work consensus under the assumptions about continuous time and zero time delay. The next work in this direction is about probability of double spend attack for blockchain with also proof of work consensus, also continuous time, but with a non-zero time delay. So this work is a generalization of previous one. It were results of me and my colleagues, and this work was published in 2020. And the next probability of double spend attack for blockchain with proof of stake consensus under the assumption of zero time delay, and it was classical proof of stake consensus without checkpoints, were obtained by me and my colleagues in 2021. And the purpose of this research is to estimate the probability of double spend attack in blockchain based on proof of stake consensus protocol with checkpoints, to find the necessary number and confirmation blocks which guarantee that the probability of attack is negligible, and to compare security against this attack for blockchain without checkpoints and for blockchain with checkpoints. Blockchain is a digital ledger resistant to unauthorized access, implemented in a distributed manner without a central governing body, maintained and managed jointly by a distributed group of participants. There is no centralization in the system in the form of financial institute, banks, or something like this. As you can see on this picture, each next block contains in its header the hash of all data from the previous blocks. So this construction is very similar to chain, and that's why it is called a blockchain. There are a lot of different consensus protocols on blockchain, but the more popular and more wide used protocols are proof of work and proof of stake. Proof of work is a consensus protocol based on large amount of hashing. And proof of stake is a consensus protocol model that depends on how much money each user has invested in the system in the form of cryptocurrency. Such users are called stakeholders. The larger stake of stakeholder, the larger number of blocks he may chance to create. Points are some control points, blocks in blockchain, which freezes the history of blockchain. It means that all blocks which are deep enough in blockchain can't be changed even if a longer alternative chain appears. There are a lot of examples of cryptocurrencies with checkpoints for both proof of work and proof of stake protocols. So such modification of proof of stake protocol is widely used. A classical double spend attack on the proof of stake protocol means that an adversary creates a hidden alternative chain which contains some alternative transaction to one of transactions in other chain published by honest miners. On this picture, you can see blockchain with checkpoints. Some block contains checkpoints, and on this picture you can see a visualization of double spend attack. This is a chain published by honest miners, and this is hidden chain published by adversary, not published but created by adversary, and adversary publish this chain even in case with this chain becomes longer than the chain published by honest miners. Adversary tries to create two alternative transactions, one in the first chain and the second in his hidden chain, and these transactions are alternative in the sense that they both spend the same coin, and that's why this attack is called a double spend attack. The attack is successful if the attacker managed to build a chain that is longer or at least equal as the chain that was published by honest miners. An explicit expression for the probability of a double spend attack in the classical proof of stake consensus protocol without checkpoints is given in this theorem, which was proved in 2020. Here, P is share of honest stakeholders. It means total stake of honest stakeholders. Total stake ratio of honest stakeholders. Q is total stake ratio of malicious stakeholders. Z is numbered confirmation blocks, and K, which is some variable, is the number of blocks created by an attacker. The results for proof of stake protocol with checkpoints are much more complicated, and the proof also needed a lot of work. This picture explains how proof of stake consensus protocol with checkpoint works, the first picture, and this picture explains how the attack is run. The main feature of such attack for this type of consensus is that adversary needs to complete this attack before the next checkpoint. So it is harder for adversary to succeed in this attack. we get an explicit expression for the probability of a double spend attack for a proof-of-stake consensus protocol with checkpoints. And as you can see, this expression is much more complicated than previous one. Their designations are all the same, except one. In this formula, we need one more designation, and is the distance between two checkpoints. This distance is measured in the number of time slots. And the numerical results given on this and on the next slide, according to our formula, show that the probability of double spend attack for proof-of-stake protocol with checkpoints is smaller than for proof-of-stake protocol without checkpoints, just as it was expected. And also, you may see, for example, when we have large adversary ratio, that the difference between probability of double spend attack for blockchain without checkpoints and with checkpoints, the larger stake ratio of adversary, the larger is difference between the probability of these two attacks. And that's all. Thank you for your attention. Maybe you have any questions. I will be glad to answer all your questions. Thank you.